Alright, so I'm just going to explain basically the entire forces unit really fast and without spelling errors. So the first thing we're going to talk about is what is a force. A force is basically a push or a pull by one object on another object. This dude is pushing this box, so he's exerting a force on the box. This dude, he's standing on Earth. Earth is exerting a force down. That's gravity. These are forces. We represent them with arrows, and the variable we use is F, unless it's a special type of force. But normally, we just have F push and F pull. If you can't tell if there should be a force, or if you feel like you're missing a force, you should use the trick F on blank by blank. You have to think of the object that's being acted on, and then the object that's exerting the force. If you can't think of the objects, the force probably doesn't exist. Now, I'm gonna list off all the variables that you need to know. F net is the sum of all forces. A is acceleration. F push, this is a push force. T is tension. The lowercase f is friction. And then from that, we have kinetic friction, Fk, and static friction, Fs. Weight. Some people call it G for gravity, but I think that's stupid. And then we have N, which is normal force. Some people call it natural force. Some people are wrong. And then finally, we have M, which is mass. Notice how I didn't put air resistance? That's because that doesn't matter. We're not doing anything with that. So we got this dude, and he exists, so he has mass and weight. His mass is 65 kilograms. We measure mass in kilograms. He has 65 kilograms basically of matter. Like, if we cut off his leg, he'd have like, let's say 62. See how his mass decreased? This guy is on Earth, and so the force of Earth's gravity is acting on him. How much force gravity pulls on him is dependent on his mass. Weight is equal to mass times the force of gravity. And on Earth, it happens to be 9.81 meters per second squared. So his weight is 608.22 newtons. The newton is actually equal to a kilogram times a meter over a second squared. Now, if he was on a different planet, this number would be different. On Mars, it's like 3 point something. Mass does not change, weight does change when you go to different planets. So we already discussed F net. It's the sum of all forces. So we're gonna go over all of the individual forces besides weight, because I already talked about weight. Let's start with tension. It's also called T, or F of T if you're a loser. It is basically the force of a string pulling something, or like a string-like thing. If I've got a pocket watch, this string is pulling up on the watch with tension. The next one is normal force, also called N or F of N if you're a loser. It's the force something exerts when it has a force exerted onto it. When you're standing on the ground, you are exerting a force that is equal to your weight onto the ground, and so the floor exerts an equal force back to it. It is reactionary. This is the opposite of calculatable, which means there's like a formula for it. Also, notice how it's called N, but that also stands for newtons. Don't get those confused. Now we're gonna talk about the fun one, friction. Also called lowercase f, or I guess F of F. Like, that's really stupid. Don't write that. There are two types of friction. Kinetic friction and static friction. Kinetic is like the way easier one to understand. It's the friction when something is sliding across a surface. And so, the ground and the box are actually really like jagged and stuff. They're gonna collide, like right here. And so, the friction, based on the amount of roughness, will exert a certain amount of normal force back onto the box. It's calculated by mu, or the coefficient of kinetic friction, times normal force. This number will often be given to you if you're not asked to solve for it, and it basically denotes how rough the surface is. This is like the amount of times the normal force hits, and then that's times the normal force. Static is a little bit more confusing. It's also calculated by mu of S, coefficient of static friction, times N. This is actually the maximum static friction. This is equal to the most force that you can push on an object and still not have it move. If you are pushing on it with less than that force, the object isn't going to move. And so when it's not moving, you know that the static friction will be the exact same amount. It is reactionary. So those are our forces. Now we need to know what to do with the forces. So we're going to draw something called an FBD, aka a free body diagram. And it's really easy to draw, and it will show you all of your forces. So the first thing you're going to want to draw is a box. It can also be a circle if you're weird. This is a representation of the object that is having the forces acted onto it. This is the only object we really care about. Now you're going to draw your forces. So the first thing that you should have is you should have weight. If it's in space, you probably won't have weight. If it's sitting on a surface, you're probably going to also have normal force. And let's say that you're pushing it this way. And then since it's on a surface, we have kinetic friction. As you can see, all of the arrows start in the middle. They don't have to be to scale. They just have to be a good representation. You should always have two. You have this one, which is for like the IB and AP people, and then you can have another, and this is called a working free body diagram. And this one, I can draw a bunch. I can write numbers. If you're gonna draw all over it, have two. You notice that we have these four forces. They can actually be grouped into pairs. Normal force and weight are both vertical forces in this scenario. Push and kinetic friction are horizontal. We can make statements about this, but we can only make them if we have a coordinate system. This basically tells you what is positive and what is negative. If you're normal, you should have right as positive and up as positive. We know that there is a net vertical force, F net Y. We also know that there is an F net X, the sum of all the horizontal forces. Don't mix these. They don't impact each other. If this gets stronger, it's not going to suddenly counteract this one. Don't mix them. So now we can say that normal force minus weight, since weight is negative according to our coordinate system, is equal to the sum of all vertical forces. The force of push minus kinetic friction, because it is pulling negative, is equal to F net X, the sum of all horizontal forces. And these are the equations that you should make once you have finished your free body diagram. And now we're going to talk about what to do with them. Newton's second law, F net equals ma. Notice we have an F net here. And so we know that F net Y equals mass times the vertical acceleration. There are vertical and horizontal accelerations. Also keep them separate. So then we can write that normal force minus weight equals mass times vertical acceleration. And now you have an equation that you can actually do something with. The exact same thing is true for the vertical equation. F push minus Fk is equal to max, the horizontal acceleration. And now you have these two equations. These are called your custom equations because you have made them according to your free body diagram. When you're solving for something, you should always notice the context first. And whenever somebody talks about knowing the context, you just need to know, is it accelerating and is there friction? Everything else is useless. If there is a net force that is not equal to 0, then there is acceleration. It doesn't mean that it's moving. It doesn't mean that it's not moving. It doesn't tell you which direction it's moving, only that it is accelerating. Acceleration is equal to F net over m. And if it's 0, acceleration is also going to be 0. Please remember this. Now we're going to get to the stuff that you actually care about, diagonal forces. I have a box. Attached to it is a string, actually 2 strings. This box is hanging. The free body diagram. We can see that one force is going this way, one force is going this way. We'll call this T1. It's tension because it's a string. And T2. And then we got weight. Let's say that the angle in respect to the ceiling is theta, and this angle in respect to the ceiling is lambda. We can solve it. This diagonal force is pulling diagonal. It's actually pulling up and it's pulling left. It has an element that is its vertical force, and it also has a horizontal force. We now have a right triangle, which means we can use trigonometry. Here is its vertical force, here is its horizontal force, here is the force itself, here is the ceiling. We know that this is theta, and so this angle is also theta. Alternate interior angles theorem. We can now use trigonometry. This is T1. For right now, I'll call this Y, and I'll call this X. This is opposite of the angle, so it's sine theta equals Y over T1. And so Y equals T1 sine theta. So now we know the vertical force in terms of the angle in T1. And this one is going to be T1 times cosine theta. Now, of course, if they gave you this angle right here, if they gave you this angle, it'd be different. So you have to draw it out yourself, and you have to figure out what angle they give you and how to put that into the right triangle. And so now we can do a new free body diagram with all of the forces, and they're vertical and horizontal, so we can work with them. Now I'm going to show you how to solve when you have too few variables. The absolute rule: leave the equation in variables or until you cannot anymore, because that makes it so much easier and that makes it often actually solvable. We have a box. It is hanging. This is going to be 20 degrees. This is going to be 40 degrees. The mass is going to be 50 kilograms. We want to know the tension in these strings. I'm going to call this one Z, and I'm going to call this one B. I'm going to draw my free body diagram. I'm going to draw it right here. First thing we have is weight, and now of course we have the tension. And so now I'm going to list the variables. First thing they gave us is mass. We will then be able to know weight from that, because it equals mg. That equals 490.5 newtons. The vertical acceleration is 0, and horizontal acceleration is 0. Just so that I know context, there is no acceleration, and there's no friction. First, we need to break up these diagonals. I'm gonna draw my working free body diagram. In fact, I'm not even gonna include weight. I know that it exists. And I know that this is 20. I know that this has a horizontal and a vertical component. It's pulling it this way, and it's pulling it this way. And I know this is a right angle, so now I have my right triangle. And same with this guy. Now I can draw my triangles. I'll start with this bad boy. Not to scale, not to angle. I know this is 20, and I know this is z. And so this is going to be z sine 20, and this is going to be z cosine 20. By this logic, I can just automatically know. I basically go through this whole process in my head. For the other one, I know that this is going to be, I named it b sine 40 and b cosine 40. I can draw yet another free body diagram. And now I can make the customized FNet equations. Start with vertical, z sine 20 plus b sine 40 minus weight. I know that acceleration for y is 0, so this is 0. I'm gonna add weight to both sides. Now I'll do x. I know that it's going to be b cosine 40 degrees minus z cosine 20 degrees. And I know that there is no x acceleration either. This is equal to 0. So now I'm going to make my system of equations. I can now solve the system of equations. I'm going to use substitution. Obviously it isn't fully solved, but you can clearly see how I could go from here. Could isolate b. I can substitute in w for this, and then I can substitute b back into this equation to find z. And those are our two tensions. There is a possibility Mr. Thompson will whip out some sort of algebraic thing that we haven't discussed, so be prepared for that, which is why you use the golden rule of keeping the variables. Now we're going to address the last part of the advanced forces unit, and also the hardest, which is ramps. This is a crude drawing of a ramp. It is at an angle of theta degrees in respect to horizontal, and there's a box on this ramp. This box is being pushed down a ramp by this tiny dude, and it is accelerating down this ramp. I'll draw on it as if it's a free body diagram. We have a weight, it's going straight down. We have the force, push force, and it is going parallel to the ramp. He's pushing it down the ramp. We have friction, kinetic friction, which is also parallel to the ramp. Now, let's draw the free body diagram for this. And this is really weird. So what we're going to do is we're actually going to rotate it. We're going to treat the surface of the ramp as if it is the floor, as if it is horizontal. And so now, instead of two diagonal forces, these are both horizontal, and weight is at an angle. We need an angle for this. We were given theta. How are we going to work with that? Let's draw the ramp, and then we have weight. And if we can extend weight to kind of look like this, because nothing's to scale in this. We notice we have a right triangle because weight goes straight down, and this is the real horizontal. This is theta. And so we know this. That's going to be 90 minus theta. We know that weight, as a diagonal, it has a vertical force and it has a horizontal force. We can draw these here. Here is its vertical force, and then here's its horizontal force. This is going straight down from the surface of the ramp. So we know that this right here, that's a right angle. This is 90 minus theta. This is 90 minus 90 minus theta. And so this is theta. So we know this angle's theta. And so now we can find all of the things. And this is going to equal w cosine theta, and this is going to equal w sine theta. And really, this is the rule that you have to remember if you don't want to have to do this every single time, is that the vertical force of weight, it equals weight times the cosine of theta, given that theta is this angle. Horizontal component of weight, weight times the sine of theta. And so now we can solve with this. Now I'm going to give you the rundown of what you need to know. Here is the stuff you should study and memorize. This is what you need to know. Friction is equal to the coefficient of friction times normal force. F net x equals max. F net y equals may. Rotate the ramp if you have a ramp. Keep it in variables until the very end. If the net force is not 0, acceleration is not 0. There's acceleration. When you have a ramp and this is the angle they're given, the vertical component of w is equal to weight times cosine theta, and the horizontal component of weight is equal to weight times sine of theta. We now conclude advanced forces.